Hello and welcome to this fifth session. Last time we were looking at hybridisation, and what I want to do today is to really continue from where we got to before, but this time really taking more of a symmetry approach to the problem. And then I'd like to continue looking at symmetry with atomic orbitals, and an interesting thing that pops up there which we can describe with symmetry arguments. So what we've got on the screen at the moment is the molecular orbital diagram for methane, and we were saying before how actually, and you can see there's a bit of experimental evidence from the photoelectron spectrum on the picture on the right showing the two different energy levels of the electrons in methane. But now just look at the diagram in more detail with regard to symmetry. So you can see on the left hand side of the molecular orbital diagram we've got the carbon valence subshells S, the 2s and the 2p, and so these have symmetry labels associated with them. A1, so A1 here is going to denote the fully symmetric spherical s orbital, same in all directions. Whereas of course the 2p orbitals, these are dumbbells with each lobe on either side of the origin having opposite phase, and so these orbitals point down one of the Cartesian axes and they have this kind of opposite phase characteristic. So the three p orbitals are all very much equivalent to each other with respect to symmetry, but totally different from the 2s, and they get this label T2. And the T there, if you like, is short for, you can think of that as short for triple or triply degenerate, the same energy. And what's interesting about this diagram is that on the right hand side the hydrogen orbitals are considered all together. So those four lines on the right hand side, labelled A1 and T2, they don't represent individual hydrogen atoms, they just reflect different combinations that we can look at all four of them together. So in that sense it's kind of a delocalized picture, always considering the hydrogen atoms together, different combinations of their phases. And so as you might guess, the A1, which was the fully symmetric s orbital on the carbon atom, A1 having this meaning of being fully symmetric, this is going to represent all four hydrogen atom orbitals being the same phase. Now you might think that's a bit weird because you might think, well, s orbitals are positive anyway. But really what we're looking at here are combinations of the s orbitals, and in these combinations they can be subtracted as well as added. And so if we've got a combination of s orbitals, is there going to be a plus or a minus in front of the orbital? And in the case of the A1 combination, they'd all be added together, so you've got this totally symmetrical arrangement. And in the case of the T2s, and in fact if you look on the picture on the top left here, so you can see on the left hand side of that T2 classification, we've got a 2p orbital, and that's on the carbon atom. So you can see that one end of it is coloured blue and the other end of it is coloured red, and these represent the opposite phases of the orbital. And you can see that of the four hydrogen orbitals, the two that are kind of on the same side as one particular lobe, for example the two that are on the same side as the blue lobe, they're coloured blue. So you might consider those to be all positive, for example. And then on the red lobe of the 2p orbital, which might be the negative phase, we'll look at the hydrogen orbitals having a minus sign in front of them in the linear combination. And so that way the hydrogen atom combinations reflect the p orbitals they're going to interact with, and that's why they carry this same T2 label. So that's a slightly more sophisticated molecular orbital diagram compared to the ones we've seen before, which have just been for diatomics. And so here we're considering groups of atoms together. And so I'll just summarize these points on the screen here. There we are. And so that is our methane molecular orbital diagram. And so actually we're going to go on to here to consider another type of hybridisation which we didn't look at last time, or at least we didn't look at in any detail, and that was sp3d2. There was I think an octahedral picture up there, but we didn't really look at it in any kind of detail. And in this particular case looking at it in the context of an octahedral transition metal complex. We've got the molecular orbital diagram for that on the right hand side, and just a few of the electrons appearing in that diagram actually. So what we have is each of the ligand atoms, which will be donating, if you like, a pair of electrons into the central metal. 6 of those, each of those putting a pair of electrons in. So these would be sigma bonds, 6 pairs of electrons, and so we can see those at the bottom of the molecular orbital diagram. So on this picture they happen to have been omitted from the ligand orbitals on the right hand side. Slightly odd. And then looking at the left hand side, here we've got the orbitals on the transition metal, and so you may recognise E, G and T2G as labels that we use for the 5 d orbitals. The E there, that denotes the fact that we've got 2 orbitals of equivalent symmetry. Remember the T from before was 3 orbitals of equivalent symmetry, and the E plus the T2, that makes up 5 orbitals, which is the d subshell. And actually, if you think about the d orbitals, there are kind of 2 types of them, aren't there? You've got the xy, the xz and the yz, and these are all very similar to each other because those lobes point between the Cartesian axes. And then the other 2 involve the squares of Cartesian axes. You've got dz squared and you've got dx squared minus y squared. So these are the ones that fall under EG symmetry. So it's pretty obvious really, just from sort of looking at the orbitals and their labels, that they do fall into these 2 different symmetry groups. So there we have the 3D orbitals, assuming it's a first row transition metal. And then the other orbitals are up higher in energy, and these represent the 4s and the 4p. So actually these will all be empty in transition metal ions. So we've got these empty orbitals. The A1, of course, you'd expect that to be fully symmetric, so that's the 4s orbital. And the T1U there, that T again, that's a triply degenerate. This represents the 2p orbitals. Sorry, well there'll be 4p orbitals, won't they, for a transition metal. So actually a different label to what we had before, but we're in a different symmetry now, so the labels aren't going to map across perfectly. Right, so just working through a few of these points here. So one thing that's quite important to bear in mind is the way we define the complex is that our Cartesian x, y and z axes, we're defining them to go through the ligand atoms themselves. So that's just the definition we follow. And so it's interesting because when you look at the diagram here, you can see that we're classifying the ligand orbitals as A1, T1 and E, and of course those symmetries are also reflected on the metal ion. We see those same ones there, but in addition there's a further one on the metal ion, and that's T2. And the T2, so we don't see that among the ligands. So where we have these sort of mismatch of symmetries, that implies that there's not going to be any interaction between the T2 orbitals, that's the xy, xz and yz d orbitals. There's not going to be any interaction. So you can see on the picture there's a kind of a horizontal dotted line showing the T2G orbitals there, unaffected in energy. So they just haven't interacted. You can see there's no dotted line on the right hand side to the ligand orbitals. So the T2s are not interacting with the ligands, but the EGs are. So the question posed here is, which d orbitals are of EG symmetry? Well, actually we've answered that already, haven't we? That's the dz squared and the dx squared minus y squared. And why are these better suited? So this follows from our definition of how we place the x, y and z axes. So as I was saying, the ligand orbitals are defined to be on the axes. So there's 6 ligands, and you can think of them at plus or minus x, plus or minus y, and plus or minus z around the transition metal ion, which is at the centre of coordinates. And so if you think about the shapes of these EG orbitals, the dz squared orbital, that's mainly a dumbbell that points up the z-axis. That's going to be pointing straight at the axial ligands. And the x squared minus y squared, these lobes are pointing on the x and y axes, so again they're pointing straight at the ligands. So they're better suited for an interaction because they're pointed directly at the ligands. Whereas the T2G orbitals, these are defined as pointing between the ligands, so not really a favourable geometry for an interaction. So again, the symmetry labels, we've covered these points really with the tetrahedral case, just reiterating that E means there's two symmetrically equivalent orbitals involved. And then a slightly more tricky question now is that what combinations of the ligand orbitals might we have, or if you like combinations of the phases, to reflect all these different symmetries, these different types of interaction. And we'll see this on the next slide. So you can see at the top of the page here we've got the different phases of the ligand orbitals, so we're showing these as p orbitals. We've got the different phases that correspond to the different symmetry labels. So perhaps not surprisingly, on the left hand side, the fully symmetric A1G, this reflects all 6 ligands having the same phase of lobe pointing towards the transition metal, so that's as symmetrical as it can be. And then with the T1U combination, so these are the ones which are going to be overlapping with 4 p orbitals on the transition metal, then these ones are aligned to one of the Cartesian axes, because of course the p orbitals are there, the px, py and pz, so they're on the axes. And of course remember that the lobes in the p orbitals are opposite phase. So if you look at the lobes on the ligand orbitals here, again they're matched up in opposite phase, and this way we get the best constructive overlap with the orbitals on the transition metal ion. And on the right hand side we've got our EG interaction here. So these are the ligand orbital phases which match up to the dz squared and the x squared minus y squared d orbitals. So if you look at the one on the left of the two, you can see that we've got on the axial, on the z-axis, we've got those ligand orbitals both with the positive phase pointing in the blue lobe. So these are going to be interacting with the main dumbbell in the dz squared orbital. But of course that orbital's also got a donut, hasn't it, around the middle? And actually the donut is the opposite phase to the axial dumbbell. So you can see that we've got this smaller interaction, which is denoted by the smaller orbital pictures. We've got this smaller interaction in the equatorial plane of opposite phase. So you can see it's the red lobes pointing in this time, and they'll be overlapping with the donut, which will be the opposite phase to the central dumbbell, if you like. And then on the far right there, we've got the ligand orbitals that can be overlapping with the dx squared minus y squared. And that's why we've only got ligand orbitals in the equatorial plane. Clearly the axial ones won't be forming any constructive overlap. And also look at the phases of the orbitals. So you can see that when you've got orbitals on opposite sides of the origin, it's like a 180-degree angle to each other, then the lobes are the same phase. You've got blue opposite blue and red opposite red. And actually that's the opposite, isn't it, to what we saw before with the triply degenerate ones. And this reflects the fact that the p orbitals, the lobes are of opposite phase on either side of the origin, whereas in the d orbital case, if you reflect one lobe through the origin out to the other side, those two lobes have the same phase, and that's reflected there in the phase of the ligand orbitals. And so again, in these notes popping up, just reminding ourselves about these meanings of A and T and E. Now, I haven't explained up until now about these letters G and U, but it's quite relevant here. So these are German words, gerade, even, and ungerade, odd. And it's to do with the symmetry with respect to inversion through the origin. And actually this turns out to be a very significant symmetry in chemistry and in spectroscopy. So you can see that G there, we see this with the fully symmetric one. So all those like phases there, if you reflect them through the origin, they just come out the same in this fully symmetric way. And similarly with the EG orbitals, again because of the symmetry of the d orbitals there, the same is reflected in the ligand phases where if you reflect them through the origin they come out the same. So they're both G's, and of course the U is the opposite to this, and this is consistent with what we see in the p orbitals, and likewise these ligand orbital phases, where if you reflect it through the origin it comes out the opposite phase, the other side. So this is the so-called odd symmetry. And so now I've got a fairly tricky thing to look at, and this is to do with the full wave functions for these different sets of ligand orbitals of the symmetry to overlap with the transition metal orbitals. So these are going to pop up on the right hand side in a moment, and we're going to look at the relative phases, how they might normalise, and orthogonality. So there we are. So perhaps the simplest one at the top, the A1G, the fully symmetric. And so because all these orbitals are the same phase, we've just got a whole series of psi1 plus psi2 up to psi6, representing the fact they've all got the same phase. And then we have this normalization term in front of it, the 1 over root 6. And that's obviously when we multiply the orbital by itself and integrate, all the cross terms will disappear, and there'll be six like terms, like psi1 squared plus psi2 squared plus psi3 squared. Each of those, because they'd be normalized functions, they'd all integrate up to give 1. So that would all add up to 6. And the 1 over root 6 is there, because once you've multiplied it by itself, that'll give you 1/6, and that will mean the overall function, when integrated over all space, will give you 1, which is the probability, of course, of finding the electron somewhere. And then the next three wave functions look much simpler, and that's because in these T1U combinations we're only actually considering two of the ligand orbitals, because only two of them are in just the right place to overlap with the p orbital on the transition metal. And you can see here, looking at them, that they're opposite signs, and again this reflects the fact that it's this odd symmetry. So you can see the way we label it, clearly the 1 and the 6, these are going to be representing the axial top and bottom orbitals, and then 2 to 5 represent the ones around the equatorial plane. Then moving a bit further down, I guess the most complicated one of all is this first EG orbital. And so you see there we had the chief interaction being on the z-axis, but the equatorial ones still having a small interaction. And so here we've got all 6 of the ligand orbitals involved. We see that the axial ones, psi1 and psi6, they're both positive, and they've got this 2 in front of them, denoting the greater interaction. And then the other 4 are all negative. And so this time we're going to normalize it slightly differently, because of course when you multiply the wave function by itself, the 2 psi1, that'll multiply up to give 4 psi1 squared. Same with the psi6, and so putting those two together gives 8, and then the other 4, when they're integrated up, they'll each give another unit onto that to give a total of 12. So the 1 over root 12 takes that into account. Multiply the wave function by itself, that gives you 1/12, and then that will divide that total down to 1 to normalize it. And then on the final EG orbital, again we can see, looking at the wave function, we've got 4 of the 6 ligand orbitals there. We've omitted 1 and 6 because there's no axial interaction. And again, if you look at the signs, you see that going from 2 to 3 to 4 to 5, which you can imagine that going around in turn, say like if you went round, say, anti-clockwise, then the orbital signs are alternating in order that they're the same phase opposite each other. They have a 180 degree angle across the origin. And in this case we would need, following the other examples, you'd expect it to be 1 over root 4, but of course that's the same thing as a half, and that's our normalization factor. So I think hopefully there we've rationalized the different forms of the wave function, also rationalized the normalization. Slightly trickier is thinking about the orthogonalization. So if we choose any two of those orbitals, any two different ones, multiply them together, they will actually end up giving 0 to show they're orthogonal. So I mean, this is particularly obvious when we look at the, for example, any of those T1s. If you multiply that by the A1, then clearly you'll have a sort of a +1 and a -1 term, given the plus and minuses in the T1 wave functions. So that will cancel to 0. Likewise, if we take the first EG there, you'd have +2 from each of the psi1 and psi6, giving +4, and that would get cancelled out by 4 -1 terms by multiplying by psi2 to psi5. And again, looking at the second EG, the alternating positive and negative will ultimately mean these are all orthogonal to A1. So that makes it so it's fairly obvious that A1 is going to be orthogonal to all the other 5. But actually we can work through the same process with all the other ones. So you can see that with the 3 different T's, for example, they don't involve any orbitals in common. So any combination of those would multiply together would have to give 0. And likewise, you can choose any other combination and work it through. It's all very cleverly defined, so they're all mutually orthogonal. And now I thought I'd have to finally talk about spherical harmonics. These are very famous functions, very widely used, and particularly relevant to us because these are the angular functions of the atomic orbitals. So remember, we define the atomic orbitals in terms of 2 angles and a distance, and those 2 angles, theta and phi, well, the functions of those angles that describe our atomic orbitals are these functions, the spherical harmonic functions. And we can even think of it in a kind of classical way as well, and that is they define the vibrations on a sphere, which kind of makes sense because, you know, we consider an atom at the most basic level, like a hydrogen atom, we consider it to be basically a sphere. It's got spherical symmetry. And we are considering the electrons as waves, and we've spoken about the orbitals as being standing waves. So it does make sense really that these orbitals are effectively vibrating standing waves on a sphere. And so that's exactly what these functions describe in the classical world. And it's interesting that these particular spherical harmonic functions are described by 2 variables which have to be integers, L and M. And of course these are our quantum numbers, the orbital angular momentum and the projection of the orbital angular momentum on the z-axis. So again, that just gives us this link between the orbitals and this kind of classical physics of spherical harmonics. And what's really handy about this, and we've kind of used this analogy before, is this analogy with vectors. And so I think we came at this in the first place because these spherical harmonic functions, these are eigenfunctions which describe orbital angular momentum. And orbital angular momentum is a vector quantity. And so it's perhaps not surprising then that we have these kind of vector characteristics with the L and the M. And so if we treat L and M as if they're vectors, we can actually make some surprisingly good progress and get some very useful results. And another fantastic thing about these functions is that they are all mutually orthogonal. So there's actually an infinite number of these. So what we have on the screen is just the first few. So at the very top there, that's like our s orbital. That's when L equals 0. Then the next level down, we've got L equals 1. And there's 3 of those. That's kind of equivalent to there being 3 possible values that M can take between 1 and -1. Of course, there'll be combinations of those, won't they, to make it real. Then the next level down, that's like our 5d orbitals, all corresponding to L equals 2. Then underneath that, we've got our 7f orbitals with L equals 3. But as a kind of mathematical quantity, these spherical harmonics, you know, they just go on forever. We can have as many as we like. So of course in chemistry we only see a certain number of subshells because only a certain number of elements, but it's kind of limitless as a sort of mathematical idea. And so despite the fact there's an infinite number of these, amazingly they're all mutually orthogonal to each other. But that's really good for our purposes because it produces massive simplifications, because we know we can multiply any 2 of these together and integrate, and it's always going to give you 0 unless the two functions are the same. Massive simplifications to calculations. And the other thing is that the e to the im phi, so you might remember these were our eigenfunctions based on the azimuthal angle, phi. All of these are naturally orthogonal. So if you think about it, if you took two different functions, two different values of m, and you multiply them together, then effectively the m's would just combine as they're in an exponent, so you just get like a sum of the m's. And if you were to integrate that over all space, which is what we do when we look at this orthogonal question, then what happens when you integrate e to the im phi? Well, that would just be 1 over im multiplied by e to the im phi. And so if you integrate that over all space, what does all space mean if you've only got an azimuthal angle? Well, as far as the azimuthal angle is concerned, all space is going from 0 to 2 pi radians. It's like a loop-the-loop round the equator of the Earth. So if you're going from 0 to 2 pi on that wave function, I mean, if you think about this idea, this Euler equation where e to the I phi is cos of phi plus I sine of phi, then that sine of phi term, if you're looking between 0 and 2 pi, of course the sine function is 0 at 0 and 2 pi, so that would disappear. And if you look at the cos function at 0 and 2 pi, it comes out as 1 both times. So when you do the integration and you take the 0 from the 2 pi, it's always going to cancel and give you 0. So again, these functions are just built to be naturally orthogonal. Now, a slight change of gear. So we've been talking about symmetry quite a bit here. And of course, these spherical harmonics are functions of a sphere. And the whole thing about orbitals and subshells and everything is we start at this looking at hydrogen. And of course, the hydrogen atom in isolation, we're basically looking at a sphere. It's the same from any direction. But of course, when we're looking at chemistry, we're dealing with molecules where we have distinct geometries involved. And of course, we've been looking at things like tetrahedra with methane, octahedra with these complexes. And in fact, you might remember when we were looking at the sp3 hybrid orbitals before, we were saying that tetrahedral arrangement, we can really think of that as being built into a cube. And so in fact, you can see with this picture on the right here, so if you look at that carefully, we've got a couple of tetrahedra on top of each other, sitting in a cube wireframe, and we've got an octahedron inside. So actually these shapes, they're all highly symmetrical and closely related. So you see that the tetrahedra there uses half the corners on a cube, and when you look at a cube, if you connect the center of the 6 faces of a cube, those become the 6 corners of an octahedron. And if you take the center of the 8 faces of an octahedron and connect those up, they become the 8 corners of a little cube inside the octahedron. So in fact, all these shapes are so-called platonic, so they're all as symmetrical as they can be. All the corners are equivalent, the edges are equivalent, the faces are equivalent, and in fact also the octahedron and the cube have this so-called dual nature. How, connecting up the centers of the faces, one goes to the other and back again. And so up until now, our discussions about tetrahedra and octahedra and cubes, for example, the point I really wanted to make, which is to do with the symmetry of these things, is that the x, y and z axes are all equivalent. No one has got any kind of special priority. Like in a cube, of course, x, y and z, ultimately they're the same distances. They mark the same distances down the edges of a cube. You can rotate a cube, say, 90 degrees, for example, and it looks the same as it was before. So it's very significant that when we're working with these symmetrical molecules, x, y and z are on a kind of equal footing. But actually, you remember, it was very different when we were in a spherical footing, because do you remember when we had an orbital angular momentum vector, because of the uncertainty principle, it turned out that the only things we could know were the length of the vector and its projection on one axis, just one axis. And that meant we had to make one axis kind of special, and we kind of made it arbitrarily the z-axis. So when we were looking at our spherical orbitals, we have a special axis, a z-axis. But in molecular systems, where we have this kind of high symmetry, the z doesn't really have any special status anymore. X, y, and z are all equal. And so now this is going to become quite relevant for our discussion of symmetry in atomic orbitals. That's what we're building up to. And so to make some progress on this, we can go back to the earlier conversions we were looking at. So you might remember when we were defining spherical polar coordinates, where we had r, the distance from the nucleus, theta, the co-latitude, measured from the North Pole, and phi there, the azimuthal angle, a bit like the longitude. Then they were related to x and y through trigonometry, so those are the equations we had up before. And so what's quite neat about this is that rather than working in this spherical way, we can now start expressing things in terms of, for example, x and y coordinates, and this becomes quite interesting, because our e to the I phi there, so you can think of that, remember we said that is cos of phi plus I sine of phi, so the Euler equation. But of course the cos of phi plus I sine of phi, using the equations above, we can express that in terms of x and y. So if you look at those x and y functions, if you divide them through by r sine theta, that leaves you with this cos of phi and sine of phi. So we can actually write e to the I phi as x plus iy over r sine theta. And of course, when we had our azimuthal eigenfunctions, they're actually e to the im phi, where m is the quantum number. And so, of course, since e to the I phi to the power of m is the same thing as e to the im phi, it follows the I phi as e to the im phi. We can express that as x plus iy to the power of m. Now, this is actually has some significance for us, because as I've just got up on the screen here, if we're looking at this kind of cubic symmetry, that implies a kind of fourfold rotation. So there are axes down to cube where you can rotate the cube around 90 degrees and the cube appears unchanged. Of course, the same goes for the octahedron and well, certainly for the octahedron and the cube, we have this fourfold symmetry. And so, if you think about the sort of x-y axes, if you were to say rotate those axes around 90 degrees anti-clockwise, the x-axis would move onto the y-axis, and then moving the y-axis 90 degrees anti-clockwise, that takes the y-axis onto minus the x-axis. So we have this kind of transformation of the coordinates when we do a rotation. But it's something very significant actually about this e to the im phi relation. So that e to the im phi, so this is our sort of eigenfunction in terms of phi. When we write it as x plus iy, this is how we define the Argand diagram, isn't it? So if you're talking about complex numbers with a real part and an imaginary part, on the Argand diagram we'd have, x as real and then y on the imaginary axis. And so it turns out that actually treating these as rotations in the complex plane, if you like, on the Argand diagram, turns out to be a very useful analogy for us working through this, as will hopefully now become clear. But before we do, just to talk another point about spherical harmonics, because we're going to have to use this extra bit of argument on the screen now. And this is a clever trick. Well, there are a couple of clever tricks we can use with spherical harmonics, because of course our electrons, we're going to be expressing the orbitals, the wave functions, in terms of these spherical harmonics. But what's really neat is that if two electrons, for example, are going to interact, if there's some kind of interaction between wave functions, it also turns out that you can express the interaction in terms of spherical harmonics. And so if you're looking at an interaction between two electron states, you can actually consider it as a product of three spherical harmonics, two of them for the electron states and one of them for the interaction. And again, that's very useful. Firstly, our idea of the spherical harmonics as vectors becomes very profitable. So you can see the picture on the right here. This is just showing vector addition. So we've got vector A plus vector B, tip to tail, addition of vectors. And then so the result of that being this sum A plus B. And so actually we can treat the harmonics a little bit like vectors in this sense. And so, for example, with d electrons, we think of the d electron as having the L, the orbital angular momentum, being 2. And of course the L there, this is the index on the spherical harmonic function. And so if we're combining two electrons, that's to say two vectors of length 2, then ultimately an interaction between those electrons could be considered as the vector sum of those two L equals 2 vectors. And when you sum two vectors of length L equals 2, the sum is going to depend on the relative orientations of those vectors. So when you've got two vectors L equals 2, the greatest possible resultant you could have is 4. But depending on the angle there, it could be smaller. So like on the picture there, it looks a little bit like we've got a resultant of about length 3 compared to if we say the vectors are length 2. But equally, if we could get a length 2, so for example, those vectors could be in the shape of an equilateral triangle, and in that case the resultant would be length 2. Or indeed, the vectors could actually completely oppose each other, and so the sum of the two vectors would be 0. And so this sum of vectors here is quite a useful analogy, looking at these interactions between electron states. And so in our particular case here, we're going to be considering looking at the d orbitals in particular. We can consider an interaction that involves a 90-degree rotation. And so ultimately, of course, when we're just considering a rotation from one orbital on top of another orbital, when we consider ultimately the three spherical harmonics together, it actually doesn't really matter if you're considering an energy or if you're talking about a transformation like a rotation. Ultimately, what we need to get at the end of it all is some kind of scalar quantity, so like some kind of a number, for example, rather than a vector quantity. And this is why we have all these vectors forming this triangle. And so, yeah, we've got this kind of so-called triangle rule here, which gives our resultant anything from 0 up to 4. And so, again, this is going to allow us to take some mathematical shortcuts. I'd like to look at the fourfold rotation in a bit more detail now. And we mentioned before how the x plus iy representation of the e to the I phi function looked rather like the Argand diagram describing the complex plane, x plus iy, that's to say x being on the real axis and y being on the imaginary axis. And that's what we see on the picture on the screen. And so, as we said, if you're going to do a fourfold rotation, which is how we're kind of characterizing our cubic symmetry, then if we're rotating anti-clockwise, that would move the x onto the y position, and also it would move the y onto the minus x position, taking that around a bit further. But of course, when you move x onto the y position in this complex plane picture, it becomes imaginary, so you'd be effectively multiplying by I. And actually, by the same token, if you rotate y to minus x, you're taking it from the imaginary to the real axis, so you're effectively dividing by I. This is quite interesting because of course when y goes into minus x, there's that minus 1 factor, but of course minus 1 is also equal to I squared. So changing y to minus x, we can both consider it as multiplying it by y squared to make it negative and dividing by I to reflect the fact that we're going out of the imaginary axis into the real axis. So combining those together, I squared over I, that's equivalent to multiplying by I, which is just what we got when we rotated the x-axis by 90 degrees. So that shows there's this common factor I that we get in rotating the coordinates. And this is very interesting because if we're going to represent this fourfold rotation using a spherical harmonic, we need to bear in mind this factor I very carefully, because of course what fourfold rotation means is that if you rotate the system 90 degrees, it's completely indistinguishable compared to what it was before. So you can't be multiplying something by I, it's got to be indistinguishable. The only thing you could multiply it by is 1, which would leave it looking the same. And actually this is relevant because of course that factor I, if you apply it 4 times, it does return 1. Because of course I squared is minus 1, so I squared squared, I to the 4, is plus 1. And so by applying this factor I 4 times, that is to say that we're applying the e to the I phi 4 times. And of course this is what we do when m equals 4. So it turns out then that if you're going to model a fourfold rotation using a spherical harmonic, you would need to have m being plus or minus 4 to represent the factor I being applied 4 times with this 90 degree rotation. And so in order for m to be plus or minus 4, the L value of the spherical harmonic would have to equal 4, or 4 or above. So we couldn't have m equals 4 with L smaller than 4, that wouldn't be allowed. And so therefore, using our vector model, this implies that our spherical harmonic kind of operator, as it were, our spherical harmonic representation of the fourfold rotation is effectively going to mix eigenfunctions whose m differ by 4. And that's again looking at all these spherical harmonics as vectors. So if you think about the orbital in its original state, then the orbital after the 90 degree transformation, if that's being connected by the operator representing the rotation having m differing by 4, then ultimately if these vectors are all going to sum up to some kind of scalar quantity, then that means that the eigenfunctions have to have m differing by 4, and that's going to be very significant for looking at how we combine the eigenfunctions when we make our orbital functions. And so looking now at the d orbitals, we might ask ourselves, are the d orbitals that we've drawn, which we drew up in a kind of spherical sense, are they cubic in a kind of Cartesian way? And so what we've hopefully established is that if we're in an environment where x, y and z are equivalent and we can do a 90 degree rotation of the system on a fourfold axis and leave it looking unchanged, then effectively that we can represent that symmetry with a spherical harmonic operator with this m equals plus or minus 4. And what that plus or minus 4 operator effectively will do is it will, as it were, connect or mix orbitals whose m quantum number differs by 4, +4 or -4. And this is quite interesting because that would imply then that the m equals 2 quantum number and the m equals -2 quantum number, when you're describing the eigenfunctions for the d orbitals, that implies that they'll be mixed together by this kind of symmetry operator. But what's neat about this is that we went through this exact process when we were making d orbitals real in the first place. Because you might remember that these are all complex functions, and this is the e to the im phi, and so to make those real, we had to take linear combinations plus and minus to produce functions that were purely real or purely imaginary. So in fact, this process of combining 2 and -2, sum and difference, we already did this in our definition of the d orbitals. But at the same time, of course, we were mixing eigenfunctions whose m quantum number differed by 4, which is also the process of making it symmetrical under these kind of cubic conditions. So by a sort of lucky happenstance, we've actually made our d orbitals cubically symmetric when we were defining them without even realizing it. So the d orbitals are cubically symmetrical. And going further than this, we can also say that the p orbitals are going to be symmetrical in the same way, and this is kind of obvious in a sense just by looking at them, because we've got 3 p orbitals, each of them point down a different Cartesian axis, x, y and z. So looking at the p orbitals collectively, it's obvious that no axis, like the z-axis, hasn't got any kind of special priority, because each orbital points down a different axis. So there you go, the p orbitals are cubic as well, and s, well, trivially that's cubic, because it's just obviously x, y and z are equivalent in an s orbital. Every direction is equivalent in an s orbital. So there you go, our d orbitals are kind of by fluke cubic. But we'll see that things are not quite so simple with the f orbitals. Now, of course, the f orbitals are defined, so what we can see up on the screen at the moment, our f orbitals are defined in exactly the same way when we look at them in the spherical basis, which is to say that we take the same linear combinations, plus and minus m and minus m, to form these pure real or pure imaginary functions that we can plot as real functions. So just like the d orbitals in that respect, but an important difference with f orbitals is that since L equals 3, we're not just limited to the +2 and -2 combination, which differ by m equals 4, but of course with L equals 3 we could have m equals +3 and m equals -1. They're different by 4, and also m equals -3 and m equals +1. Those are different by 4. So since they're different by 4, then we ought to have those mixed up, interacting with each other, through our 90-degree fourfold rotation symmetry. Now this is a problem, because when we define the f orbitals in this kind of standard spherical way, we didn't try and do this. And so it follows then that the f orbitals, as they're most normally defined, are actually not having cubic symmetry. So x, y and z are not equivalent in this sense. So actually when you look at those pictures on the right there, these are defined in the spherical sense, you can see then that kind of z does have some kind of a priority here. We've got that fz cubed orbital pointing up the z-axis. We haven't got anything like that along any of the other axes. So again, that makes z look special. And so again, like on the opposite end, if you go right to the top there, you can see that those lobes are all there in the plane perpendicular to the z-axis. We don't see all those lobes kind of fanned out perpendicular to any other axes. So again, it does look rather like the z has this kind of special priority, which of course is inherent in our spherical model. But it is possible to formulate f orbitals in such a way that they are cubic. And so what we have to do this is we have to explicitly mix the 3 and -1 eigenfunctions and the -3 and +1 eigenfunctions. And actually, having gone to that trouble, we then of course have to form real combinations of these as well. So I'm not going to inflict all the linear combinations of functions on you, but what is very neat, I think, is just looking at it pictorially, because once you do go through this mathematical process, you get the orbitals here that are shown on the right. So I think you don't even need to look at the functions. You can just appreciate by looking at them that these are going to be cubic. And so the first thing we can ask ourselves is, which of these orbitals are unchanged from the original ones? So you remember I was referring to fz cubed before. Well, there's the fz cubed at the bottom there, so that has been preserved. And another couple were preserved as well. So second down on the right hand side, fxyz. Well, we saw that before as well when we were looking at the spherical symmetry. But if you just look at the name fxyz, you can kind of see that, you know, all three Cartesian axes labels are there, all in a sort of equivalent, all raised to the same power. So it kind of perhaps shows that particular orbital doesn't show, you know, the z having any particular priority. Let's see. So now looking at the fz cubed, you can see that the way these orbitals have been redefined, we also now have an fx cubed and an fy cubed. So these are all very similar, they're sort of identical looking orbitals, just pointing along different Cartesian axes. And so defining them in this way, you can see that, as it were, all of the Cartesian axes are represented. And so z isn't getting any special priority here. We've got that same sort of cubed orbital along all three axes. And yeah, and then there's the x, y, z there as the axes are on an equal footing. And the other one that's unchanged is second down on the left hand side, fz x squared minus y squared. We had that before as well. But if you look at some of the new ones that have cropped up, look at the two at the top. That's an fx multiplied by the difference between two squares of the other axes, and the other one is fy multiplied by the difference of the squares of the other two axes. And so when you compare those two with fz and the difference of the two squares of the other axes, you can see that when you look at those three together, as it were, x, y and z are again on an equal footing. It's all fairly symmetrical, the way you've got the three Cartesian axes involved. So it's rather clever how we can mix up the wave functions, the eigenfunctions, using this idea of m being different by 4, make the wave functions real, and they just kind of materialize in these new shapes where the x, y and z are all on an equal footing. So there you go, slightly obscure, I'm afraid, but actually you do sometimes see these in books. I think if you look up f orbitals and what they look like, I think probably 9 times out of 10 it will show you the spherical ones, but you know, you may come across these as the cubic f orbitals, and so now you know where they come from. They come from this explicit mixing that represents m differing by plus or minus 4 being mixed together by the 4-fold rotation. Then we take linear combinations to make them real, and then as a result of that, so it just goes to show, doesn't it, that as a result of that idea of this 4-fold rotation being reflected by a spherical harmonic operator with m plus or minus 4, how when you do that, it just works, doesn't it? It just drops out so that they're sort of manifestly x, y, z equivalent, as it were, equal footing. So there you go.